Alrighty. So chapter 9 is all about circles, folks. Yay! New shapes! So there will be certain parts of circles that you know, like there's stuff you know, and we're not gonna hover and spend a lot of time on the stuff that you do know. Yeah.
Should we maybe back the time?
If you still think you'll study from it, you can keep it. I'll put the basket out before the end of the class if you're ready to give it back. Okay, so let's see. If we were only going to talk about circles, like what is a circle and what is its area and what is its circumference, that would not be a very long chapter. So what we're going to do is actually talk about what happens when we have circles interact with other shapes. Like, what happens when we throw a line into a circle or a couple lines into a circle? We create angles. What happens when there's angles inside of circles? What happens when there's triangles inside of circles? Or triangles outside of circles? Okay, so what's interesting with that is that these are some of the most basic geometric fundamental truths that our world actually was built off of. Before a numeric system existed, weren't there shapes? I think there were shapes probably before there were counting systems, because people communicated by drawing shapes on walls before they started, doing other things. Like hieroglyphics. Yeah. All right. Don't get me started. Okay, so if we take a line or a line segment and we interact it with a circle, there are a couple different ways that we could call these. One of them is a chord. So a chord is a segment whose endpoints are on a circle. Well, that's this thing right here. Have you heard of a chord in our body? Ooh. Okay. Umbilical cord, vocal cord, and spinal cord. Okay. So check it out. The vocal cords. Okay, if you look at the throat, the throat is an approximate circle, okay, and this would be a chord, right? It attaches to either end of the circle of your throat. When you blow air through that, they vibrate. The vibration makes it, okay? Here's another image of it, okay? Now, a diameter, I know you know that word, right? Okay. Well, a diameter is a chord. It's a special chord. It just happens to go through the center. So it's a special chord. So special that it has its own name. Okay? And what makes it special is that it always goes through the center. What do we call half of the diameter?
The radius.
Awesome. So the radius is half the diameter. So it is a line segment from the center to the edge of the circle. How many radii are there in a circle? An infinite amount of them. Very good. Because there's only two in a diameter, but I could draw a radius over here, I could draw a radius over here, here, infinite amounts. That is a lot of slices of pie. All right. So what else? Aha. Secant. Ooh. It's like a guitar. Does that word come up in guitar?
I don't know.
Okay. I don't know. Like in lessons or something? Okay.
Brad's Guitar Hero Day.
A secant is like a chord, I suppose, except that it goes on forever. Okay, so whereas the chord kind of stopped at the edge of the circle, the secant does always go on forever, so the secant is always a line, not a line segment. I try to remember secant because it starts in S, and I say that it slices through a circle. My way of remembering chord is that I think of vocal chord, I think of what that looks like, and then that helps me remember that that's different from a secant. And have you heard the term tangent before?
Yeah, that's another one.
Okay. Oh, wait a second. I've worked with you in the word tangent before.
Yeah.
Oh, okay.
Wow, small world.
Did you know that there's another way to use that word?
Apparently.
Okay, so besides using tangent as a button on your calculator and doing opposite over adjacent, tangent is what a tangent line is a line that just touches the edge of the circle. This is probably the most valuable line that comes in contact with the circle because it has a very special relationship with the circle when it is tangent. A secant is actually also a trig function. You just won't learn about it until you get kind of like to pre-calculus. But there are a total of 6 trig functions, not just 3. You've learned the first 3, the other 3 come later in math. All right. So, looking at this picture, could you categorize the different, lines and line segments?
Yes.
Awesome. What is CD?
Chord. Radius.
This would be a radius. Right here. Okay, what about D to E?
Diameter.
Ooh, okay. If you answered this as chord, it would not be wrong, but it is a special chord. It is the diameter. You will always know if it's a diameter because we will tell you. You see that symbol right there? That is, I'll blow it up. It's a circle with a C to indicate that the center of the circle is at point C. So if you see a chord going through that point, it is a diameter. What about AD? That is a secant. What about BD? Yep, and notice this thing on top, right? It's not going on forever. It's a line segment from B to D, so therefore it is a chord. And AE is a tangent. Awesome. Okay. Easy peasy, but make sure you know those words. Because in a couple days or a week or so, we will learn some formulas for like the size of angles. And there's a formula if it's a tangent together with a secant. There's a different formula if there's a secant together with a secant. There's a different formula if there's a tangent together with a tangent. So you just have to know the difference of them. Okay, so if circles interact with other circles, just wanted to give you some visuals of what that could look like, right? They could overlap. And if they overlap, they could have intersection points. Let's see, they could just be what we call tangent circles, where they literally just touch each other at one point here. This is also tangent circles, but one's inside of the other. And then these have 0 points of intersection. Do you think there could be any other combination of ways that 2 circles could intersect? Like, could we have 3 points of intersection?
No. Yeah. Oh, no.
Like, I want you to think about sliding, 2 lifesavers over each other and being like, okay, can I get this to intersect 3 times?
Just with 2 circles?
Just with 2. Sam's saying, what if they're the same size? Then how many points of intersection would there be?
1.
Infinite. Yeah, or infinite, really.
Well, with the one on the... Oh, no, never mind.
All right. What else? Okay, so we call these tangent. They have an exterior tangent because they're like outside of each other. This is internal tangent. This is called concentric. You're going to see that word. So if you see it in the homework, just be aware that that's some new vocabulary. It's like a target. All right, so let me ask you this question. If the radius of the big circle is 8, and the radius of the little circle is 5. How big is that red line?
3.
Oh, good. Very good. That's fast. Everyone feels okay with that? Okay. Very good. All right. because that would be 3. All right, super. What else? Suppose you have 2 circles. You can have what you call a common tangent. And we will see that today in the homework. We will see some common tangents. There's a couple different ways they could look. So essentially they could be tangent to both of the circles at the same time. I just want you to imagine a tricycle, right? A tricycle on the ground is the common tangent, right? It doesn't matter that the front wheels are smaller than the back wheels.
How about the back wheels?
Or whatever. This is also a tangent. Now, if I have 2 circles and I want to draw all the possible tangents, anybody have an idea of how many there would be?
A lot. 3. 2. Infinite.
No, it'd be infinite.
7. 4.
You could have one here. You could have one here. You could have one like that. And you could have one like that. That wasn't drawn very good. Okay? So you could have a total of 4. All right. Now, I want to show you something. I've got this cool little applet.
These are the rounds.
All right. Tangent. Point of tangency. So take a look at this cool little program. We can kind of play with this. I can move these points around. We're going to get to the part where we talk about angles and stuff like that, but what I really want you to notice, I'm going to move this to where it lines up right with the C. And now there's only one point. It is the point of tangency. And what is the size of that angle?
That's a 90 degrees.
Okay, it will always be 90 degrees. That is a really, really important part of tangent lines. It's a really important part of the relationship with points of tangency. So the radius in any tangent line will always form a 90-degree angle. So even if I was going to draw in another radius, if I had a tangent that was tangent right at that point where the radius meets, I know for a fact that these would both be right angles. Okay, and that can be anywhere on the circle. That's an important part of a tangent, and it makes it useful. So that's a new theorem. All right, what we can do is we can say that if a line is tangent, so if we are told that it is tangent, then we know that the line is perpendicular to the radius, and vice versa. If we know that it's 90-degree angle, then we can call it a tangent. So a line is tangent to a circle if and only if the line is perpendicular to the radius at the point of tangency. So this is your tangent. And this right here is your point of tangency. Point of tangency. Tangency. So you will be asked to do kind of mini little proofs with that. Where you'll be given a situation, maybe with some numbers involved, and you'll be asked to prove, hey, are these numbers enough for you to know, yes, this is a tangent, or no, it's not a tangent? I'm going to come back to this in just a second. So this is what I'm talking about. So if we look at number 1, if we have this particular triangle in the context of a circle. So I've got a radius here. I've got a line that goes all the way out. And then I've got another line. If I want to know whether this is a tangent, I need to kind of have a proof to say, yes, in fact it is, or no, in fact it's not. So if we look at that triangle, do you notice anything about the side lengths? Oh, okay. So a 3, 4, 5 is a right triangle special triple. Ooh. All right. Special triple. So therefore, I know for a fact that this here, right here is my hypotenuse. So therefore, that angle right there would be 90 degrees. And now I can call this a tangent. So I can say, yes, In fact, DE, is tangent. Because DE is perpendicular to DC. So it's not a particularly long proof. It's just using that fact. So number 2, similar question, slightly different set of information. Kind of a not quite complete set of information. Do we know how long this edge is?
No. It's a radius.
Ah, there's like a hidden radius, isn't there?
Oh, God.
Look at this right here. Isn't that going to be exactly the same length as that? That's something you're going to need to start looking for. All right, you're going to need to look for where there's radii that maybe aren't like waving their hands at me, but I kind of need to see them.
This is also a 3, 4, 5.
This is also a 3, 4, 5 because once you recognize that this is 6, this whole thing is 10, and it's also a 3, 4, 5. Very good.
I guess I should recognize that before you actually recognize it. Can you trust that or not?
You actually, okay, this is a good question. The answer to that is actually no, because I don't know that it's a right angle. Right? So just because I have the 6 and the 8, I don't know that it's the right triangle, so I can't just assume that it is. So I do have to know all 3 sides to then go, oh, that means it's a right angle. All right, we will finish these up on Tuesday, and 9-1 is your homework. You should be able to do parts of it. Maybe give it a shot.